Hey guys, welcome back. Welcome back to Vedantu's JEE channel. How are you all? How are my students? Especially the students who are moving from 11th standard to 12th standard. That means students who are targeting JEE 2021. As you are aware that this is specifically the time when we all the teachers on Vedantu's JEE channel come to meet all the students who are moving from 11th to 12th standard. Okay, so guys, are you a new student on this channel or are you a regular? Do tell me that, not in the chat box. I would like to know that in the comment section. Okay, so I welcome you all once again. Today's session is going to be the continuation of our very first chapter, that is electrostatics. And this is the second part of Gauss's law. And I'm going to tell you the applications of Gauss's law here today. Okay, guys. But before I go forward, let me start off with my introduction, guys. Okay, this is me, your Suri sir. If you do not know me already, I'm known as Mogambo on this channel. Why? Because when you will crack this examination of JEE, guys, yes, Mogambo khush hoga. So do make me proud when you are going to appear for this examination next year. Crack this examination, and for that, obviously, I would want you to be regular in my classes so that your preparation is always on the track. Okay, cool. And if you are new, obviously, you would like to know the timetable, the schedule that we follow, and also the teachers who are going to teach you in this series. So guys, let me introduce you to the Vedantu's team here for all of you. This is Harsh sir, this is me, and this is Arvind sir. Well guys, Harsh sir is your chemistry teacher, Arvind sir is your maths teacher, and this poor fellow is me. I would like to try to teach you guys physics. Okay, now more importantly, the timings are important, guys. Very importantly, I would like you to keep this time reserved and kept as a reminder in your cell phone that every day at 9 p.m. we meet for discussion of theory as we are meeting today. Okay, and similarly at 8 p.m. on specific days, which are basically Monday, Wednesday, and Thursday, we meet for discussing MCQs. Okay, in fact, in my previous session on the last Monday, we tried the Menti quiz also. Okay, yes, I know if you are new, you are not aware about the Menti quiz, but you will get to know. For that, you have to be regular on the channel, guys. Okay, so please remember this time slot, 9 p.m. every day and 8 p.m. on Monday, Wednesday, and Thursday. Okay, these are the teachers. This is the time schedule. Very simple to remember. Keep it in mind and be regular in the channel. Okay, and if you are a student who's targeting for JEE 2021, a good news for all of you on Vedantu's platform, guys. What we are doing, we are basically are having a batch specifically targeting the next year's JEE. And if you want to enroll for that, by the way, free of cost, you can enroll just by going on this link. Don't worry, you don't have to type this link. The link is available in the description box of this video. Okay, guys. So in the description box, you will find the link of this batch where you are getting a lot of number of hours of teaching, a lot of master teachers who themselves have walked the path, have been to IITs, including me obviously, and numerous ample number of tests, I would say, and assignments as well. Instant doubt solving session. You can watch the replays and recordings if you miss a class, a lot of quizzes and previous paper analysis. So guys, I don't think there is any reason you should not join it. So right now, after the session, go on this link, click enroll, and come for the classes there. Okay, guys. Also, if you are new on the channel, yes, I would want you people to subscribe as well as press the bell icon. Why? Because you don't want to miss out on any of the sessions which are happening here. We don't just come to teach you guys physics, chemistry, and maths or biology on Vedantu's platforms. Rather, we also come up with a lot of interesting content. We come up with motivational session. We come up with a lot of interesting stuff over there. By the way, tomorrow me and Arvind sir are coming live in the evening. If you want to know at what time we are coming live and what we are doing, we are basically going to do a kind of a jugalbandi session where we are going to compete. In what sense? You know that Arvind sir is an IIT Roorkee pass out. I am an IIT Bombay alumni. So there is going to be a healthy debate, or not exactly a debate, it's going to be a kind of a roast session which we are going to have, and that's why we have precisely called it IIT Roorkee versus IITR session. Okay, IIT Roorkee and IIT B session, IIT Bombay session. Okay, so tomorrow around evening 5 o'clock we are going to come live. We are going to do this session, so don't miss out on that, and do come and watch us both live competing, and a healthy competition for all of you guys. It'll be fun, definitely. Okay, cool. Now guys, moving on and coming to the class topic, which is Gauss's law and its application. So if you were there in my previous class, you are aware what exactly the Gauss's law was. Let's have a quick recap of that thing first. Gauss's law is basically an alternative method to find out the value of electric flux, and more importantly to find out the value of electric field at a given point. Yes, Gauss's law is something which is related to electric flux, but its major importance is to find out the value of electric field. Okay, that's what we are going to do today in terms of applications. So guys, this is what we studied previously in my previous session. Yes, this is the statement. What you see here is basically the Gauss's law statement, which says that the flux through any closed surface is equal to the total charge enclosed divided by epsilon naught. So guys, if you see this envelope, which we are calling as a Gaussian surface, it's obviously an imaginary surface. Inside it, if you have a certain number of charges, then if you want to talk about the net electric flux, what is flux? The total number of field lines which are crossing this given enclosed surface. That total number of flux, or the total amount of flux, is given by the net enclosed charge divided by epsilon naught. So if you want to know how much is that value going to be for the given case over here, all you have to do is find out the net charge over here. So guys, you can see that there are total three charges available. One is 2q, other one is q, and other is minus q. So you can see that from here plus q minus q gets cancelled, and very simply you get the value of the net flux from this surface as 2q by epsilon naught. You can also call it the net outgoing flux, because this value is coming out to be positive value, and outgoing flux is what we consider as positive because the overall charge is positive. So that's why field lines will be coming out of this Gaussian surface. Okay, so far so good. We did a lot of questions based upon Gauss's law in the previous session as well, and do not worry, when we are going to meet again on Monday for the MCQ session, that is when we are going to solve a lot of questions based upon Gauss's law once again. But now the time is actually to talk about the application part. So guys, as I told you, the Gauss's law's main application, or its actual importance, it's to find out the value of the electric field at a given point. So the major part, or rather I should say that the a very important step when we are doing the application part by in order to find out the value of the electric field, there comes a very important step, and that is basically to choose the Gaussian surface. A Gaussian surface, as I told you in the previous session, is basically like a 3D envelope. Okay, it could be a sphere, it could be a cube, it could be a cylinder, it could be a cone, it could be any 3D envelope. It has to be something which is going to enclose the charge inside itself. So the question first lies, before that step comes in a derivation, is to understand how do we choose a Gaussian surface. Okay, so there are certain things that we have to keep in mind. The very first of that is, generally you would want to pick a surface with the same symmetry as the charge distribution. That means what? If you have a spherical symmetry, you would want to go for spherical Gaussian surface. If you have a linear or cylindrical arrangement of charge, you would want to go with the similar kind of Gaussian surface. Okay, so that the magnitude of electric field, the idea of choosing such Gaussian surface is basically the reason, which says that it is done because we want the magnitude of electric field to be either constant, or we want it to be zero over the Gaussian surface that you are going to choose. Okay, I'm going to tell you till when the Gaussian surface is going to expand, till what point it's going to stay. Don't worry, that those points are coming. Okay, so based upon this, we can say that if you have a spherical arrangement, if you have a spherical charge body, you would want to go for a Gaussian surface that is spherical and everywhere equidistant from the center and has the same magnitude of electric field everywhere. Similarly, for cylindrical symmetry, as I said, you're going to choose a Gaussian surface which is cylindrical. But if you have a planar symmetry, you would want to choose a box, or you can say a cylindrical kind of surface which will look like a box, and it's going to be such that some of its sides will be parallel to the surface. I'm going to show you how it's going to be done in about few minutes from now. And a very important point is the last point over here, okay, and that says that the point where you would like to calculate the value of electric field, that must lie on the Gaussian surface. So basically, if you try to keep these 2 points in mind, the 2 points are very simple to be kept in mind. One, you want to basically choose the you want to choose the Gaussian surface in such a way that either the electric field is constant or it is zero over the surface. Also, the surface is going to be chosen in such a way that the value of uh, rather I should say the angle between electric field vector and area vector will either come out to be 0 degree, or it is going to come out to be 180 degree, or it is going to come out to be 90 degree. What I'm trying to tell you guys here is that either your electric field vector and area vector, they are going to be perpendicular to each other. It could be a small area also, or they are going to be anti-parallel or parallel. The benefit would be when you're going to write the flux value, whenever we write the flux, it will involve a cos of theta. So this cos theta will either be 0 if you are choosing the angle to be 90 degree, or it will come out to be plus 1 or minus 1. So basically it will be easy for us to find out the value of the flux and eventually the electric field. And also the next point, which says that the point where you are interested in finding the electric field intensity, that should be a part of the Gaussian surface. It should lie on the Gaussian surface. So your Gaussian surface will extend only till that point where the point where you are interested in finding the electric field is existing. Okay. Again, a lot of things said, but things will be understood properly when we are doing some derivations here. Okay. So what are we going to do in terms of application of Gauss's law? We are going to find out the electric field due to these objects. We are going to talk about the uniformly charged solid sphere. We are going to speak about uniformly charged spherical shell, or you can say hollow sphere. We are going to find out the electric field due to a infinitely long charged rod, and finally we'll speak about uniformly charged infinite sheet again. Okay guys, so let's go one by one and speak about uniformly charged solid sphere. So the first one is the case where you are finding the electric field outside the sphere. This is basically an exterior point. So you can see that the boundary of the body is lying till here, and it's a uniformly charged solid sphere. That means charge is existing inside the body of the sphere also. So this is basically the surface of the sphere, and this is somewhere, say the point is where we are interested in finding the value of the electric field. So this is that point P, which is basically at a, or say this is the point P, which is basically at a distance small r from the center of the sphere. Okay guys, so as I said, if the body whose electric field is to be found, if it is spherical, the Gaussian surface is also going to be spherical. So for the radius small r, I have drawn a Gaussian surface here, which is basically a sphere. Okay, so this Gaussian surface is basically spherical. Now, as per the previous 2 points which I spoke about, we are choosing it in such a way that, say over here, if I choose a small area vector, then that area vector dA is here, and everywhere this is going to be the situation. Wherever you go and choose a small area, the area vector and electric field vector are making an angle of 0 degree. That's what we want to. Okay. And secondly, the point where we are interested in finding the electric field is lying on the Gaussian surface. These are the 2 points that we care about. Okay. Now what do you see there? If the charge which is there in the entire sphere is capital Q, that's the entire charge which is there in the sphere, then we can say that the entire charge is enclosed right now in the Gaussian surface, because the entire sphere is enclosed in the Gaussian surface. So if we are interested in finding the value of the flux, so for a small area, that flux can be written as E into dA, and angle is already 0 degree, so we are not increasing the number of steps. And because this is the flux due to a single small area, we are going to integrate it to find out the net flux. And this basically should be equal to the total charge enclosed divided by epsilon naught. Now, as you know that electric field is same at all the points which are lying on the Gaussian surface, so E will come out, and it's basically an enclosed surface, so that's why enclosed integral, and this is what is happening. Okay. you want, you can write down cos 0 also, so that cos 0 is 1. And the entire area of the sphere is what we are going to integrate it to, that is 4 pi r square. Which sphere? The Gaussian surface sphere. Okay, this is basically the Gaussian surface whose radius is small r. So that's why 4 pi r square is the area of the Gaussian surface, and the total charge enclosed is of the entire sphere divided by epsilon naught. So E, and the integration of this will come out to be A. Limits will be put from 0 to 4 pi r square will be equal to q by epsilon naught. So this is E into 4 pi r square going to be equal to q by epsilon naught, or you can say it is E, which is equal to q by 4 pi epsilon naught into r square, or in very simple words it is nothing but k q by small r square. You remember this? We did this derivation also to find out the value of the electric field because of a spherical body outside the sphere itself. And say in the similar situation, only if I say that if r becomes capital R, then the Gaussian surface will be overlapping with the surface of the sphere, and your electric field will come out to be k q by capital R square. I hope you guys remember this expression. Okay, so we have our first and our second points being covered here itself, and now we are going to talk about the point which is lying inside the sphere. So guys, what you see here, say this is the point P which is lying inside the sphere itself, and that's why the Gaussian surface is again a spherical surface, but it is inside the uniformly charged sphere. Okay, so it's a Gaussian surface, sorry. Okay, so now it is clear to you that the Gaussian surface is lying in such a way that it's enclosing the point where we are interested in finding the electric field. But more importantly, if the entire sphere has charge capital Q, maybe the enclosed charge is only small q in the Gaussian surface. But because it is an interior point, so now we are interested in finding the electric field at this point P, for which still we can say that the electric field, if it is going to be in this direction, then the small area vector is also in the same direction, that is dA. Okay? That means still the angle between E and dA is going to be 0 degree. So anywhere if you choose that area vector over here on the surface of the sphere dA and electric field, they are going to make an angle of 0 degree. Okay guys, now first thing first, if we try to find out the value of the charge here, we can say that the small q charge divided by its volume, that is 4 by 3 pi small r cube, will be equal to capital Q upon 4 by 3 pi capital R cube. So 4 by 3 pi gets cancelled and small q comes out to be q r cube divided by capital R cube. Okay, so that's basically the amount of charge which is enclosed inside the Gaussian surface. And now we'll write the flux as the integral of E into dA into cos of 0, which is equal to Q enclosed by epsilon naught. And how much is Q enclosed, guys? Q enclosed is nothing but this small q only. Okay, so let's do that. So E being constant comes out, integral of dA again from 0 to 4 pi r square will be equal to capital Q r cube by capital R cube times epsilon naught. Okay, Q in by epsilon naught it is. So this is E. The integration of this, as you know from the previous part itself, will come out to be 4 pi r square equal to Q r cube by epsilon naught r cube. So what we see here, r square cancels this r cube and only r will be left here apart from uh, q epsilon naught and r cube. So you have electric field as 1 upon 4 pi epsilon naught q r by r cube, or simply electric field comes out to be kqr by capital R cube. Okay guys, you remember this expression? We did that when we were talking about the electric field in the electrostatics part. Okay, so this is our expression inside the sphere. This is our third part of the spherical body, which is non-conducting and has uniformly distributed charge, and these two were the interior cases over here. Okay, these two were your interior cases. KQ by small r square is outside the sphere, KQ by capital R square at the surface of the sphere, and this is outside the sphere. In fact, let me try to make you recollect the graph which we were drawing over there earlier also. Okay, so yep, so if I try to plot a graph between electric field and r vector, then this is your capital R. So from this value is basically kq by r square. So if I start from the center of the sphere till the surface, the electric field is going to be proportional to r. Yeah, and after that it's going to become inversely proportional to r square. That's what we know it. Okay, this is where it is kq r by r cube, this is where it is kq by small r square, and this is where it becomes maximum kq by r square. Okay guys, so this is basically the expressions of electric field due to a uniformly charged solid sphere. Okay guys, so I hope you guys are getting the idea how we are using a Gaussian surface over here. We are choosing the point as per the 2 points which I told you here. Have a look at the points once again, point number 1 and point number 2. Have a look at the 2 points once again. Okay, okay, so this is very important for us to keep in mind that the electric field vector is chosen in such a way, or rather the Gaussian surface is chosen in such a way that either this happens or this happens. Secondly, the point must lie on the Gaussian surface. Okay guys, so now moving on, we'll speak about the uniformly charged spherical shell, or you can say a conducting sphere also. So again, if I speak about the sphere, first of all the charge is only lying on the surface of the body of the sphere, and the point which we are interested in finding the electric field P is obviously lying on the Gaussian surface. So this is your Gaussian surface as always. Again, it is spherical, and you can see that if I choose any point on the Gaussian surface where I try to write the area vector dA, it's basically going to have the 0-degree angle between area vector and electric field vector, and entire charge is enclosed. So for an exterior point, if we try to write the flux, again very similar to the previous case, which was uniformly charged spherical body. So integral of E into dA into cos of 0 degree is going to be Q enclosed by epsilon naught. So electric field is obviously uniform, its value is same at all such points. So I'll take it out of integration, it's a closed integral. Okay, and integration of dA will be done from 0 to 4 pi small r square. Q in is the total charge enclosed divided by epsilon naught. You know that this will integrate to give you 4 pi r square, which will be q by epsilon naught, and we'll get the value of electric field as q upon 4 pi epsilon naught into r square, or simply E will be equal to kq by small r square. You remember that the case for a solid sphere or a hollow sphere came out to be the same, and that is what is happening here as far as you are outside the spherical body. And if we talk about the second case, when R becomes equal to capital R, your electric field value at the surface will become kq by capital R square. Okay, so these are very similar cases as we talked in the previous object, and now the difference that we are going to see is basically for the case when you are inside the sphere. So you see that now you are inside the sphere here at point P, and if you will see, there is no charge which is enclosed inside the sphere because it's a uniformly charged spherical shell, or you can say it's a conducting sphere. So the charge is only residing on the exterior surface, only residing at the outer surface over here. So if the charge is only residing on the outer surface, then even when you choose a Gaussian surface over here, even if you choose this as your Gaussian surface, okay, so what it encloses is no charge. we say that q enclosed is equal to 0. So when we try to write the flux, which is going to be q in by epsilon naught, so we'll write the flux as integral of E dot dA, which will be equal to q in by epsilon naught, but q in is basically 0. So if the flux is becoming 0, then in this case you can see that the area vector of the Gaussian surface is not going to be 0. So this basically implies that only and only the electric flux is going to come out to be 0 when there is no electric field inside the sphere only. Okay. So remember, whenever we are dealing with a conducting surface or a charged shell or a hollow sphere, you can say, then the electric field inside the sphere is going to be always 0. And if you remember, we used to draw a graph also to tell the same thing. So if this is capital R, this is kq by r square, and if we try to plot the graph here, so this is the value till the surface becoming 0 and remaining 0 till here. From here it becomes suddenly kq by capital R square and then varies inversely proportional to 1 by, or inversely proportional to r square, or you can say 1 by r square proportionality. Okay guys, so this is your uniformly charged spherical shell, both the cases. This was case when you were outside the sphere or at the surface, and this is when you are inside the sphere. For an interior point, electric field will come out to be 0. Please keep it in mind. Okay. Now guys, comes the next object, which is uniformly charged infinite rod, for which we say that the charge density is, say, lambda. Okay. Why we are defining the charge density? We are defining the charge density lambda, which is actually total charge upon total length. So as you can see, because it is an infinitely long object, so you do not know how long it is. So instead of speaking in terms of q, you would prefer speaking in terms of lambda. Okay guys, so here if we have a look closely, it's a straight infinitely long charged sphere. So obviously when we speak about such case, the Gaussian surface is to be chosen very smartly. I would want you people to remember the Gaussian surface that we are choosing for all the objects. Okay, so if you look at this guys, this Gaussian surface is a cylinder which is enclosing the conductor or the charged body, charge infinitely long rod, only till this length. Say this length of the rod which is enclosed is L. Okay, so if we want to find out the enclosed charge q in, it's going to be lambda into L, very smoothly. Okay, so q in is to be found very easily as lambda into L. Now if you look at the Gaussian surface closely guys, in the cylindrical surface, it's a 3D envelope. Yeah, you can see it's a 3D envelope, but in the 3D envelope basically there are three different surfaces. The top surface, which is a, you can say, a disk. The bottom surface is also a disk or flat surface, and there is a curved surface of a cylinder. So there are total three surfaces. So if you look closely guys, from this infinitely long charged rod, if you look at the direction of electric field, the electric field is going to go out radially in all possible direction. Yes or no? You know this. This is how the electric field vector is going to go in all possible direction. So if we talk about the topmost surface, so the area vector of this topmost surface is along the direction that is parallel to the rod itself, or you can say the charged element itself. But the electric field vector is going radially outward. So you can see that the angle between area vector and electric field vector is 90° here. And similar is the situation at the bottom surface also. The area vector is going downward and electric field vector is going radially outward, so that the angle between both of them is 90°. But if you look at the curved surface guys, this is where I want your focus now. On the curved surface, if I choose any small elemental area here, then the area vector and electric field vector are enclosing an angle of 0°. So if I'm interested in writing the flux, which is basically closed integral of E dot dA, and is going to be q in by epsilon naught, then this closed integral can be divided into three simple integral as integration of e into dA for say surface 1, this is surface 2, and this is surface 3. So this is e into dA into cos of 90 degree for surface 1 plus e into dA into cos of 0 degree for surface 2. You can see that angle is 0 degree, and last is simple integration of e into dA into cos of 90 degree for surface 3, and we know that cos 90 is going to be 0 degree. I told you in the beginning only we choose a Gaussian surface in such a way that the point where we are interested in finding the electric field, say this is the point which is at a distance r. Okay, so this is that point which is at a distance r from the charged body, and the chosen Gaussian surface is giving us the desired result because it is keeping the electric field either parallel or perpendicular to the area vector. So these two integrations are going to become directly 0, and from here E being a constant comes out and integration of dA is left, and the enclosed charge, which is nothing but lambda into L, will be divided by epsilon naught. And you know that surface 2 is nothing but curved surface, so curved surface area is going to be 2 pi r into L, because this is the radius of that curved surface, which is basically also the curved surface area of Gaussian surface. So E into 2 pi r L after integration will be equal to lambda L by epsilon naught. You can see L getting cancelled. Electric field comes out to be lambda upon 2 pi epsilon naught into r. You can multiply it by 2 and divide it by 2, so that we have 2 lambda upon 4 pi epsilon naught r, or you can say electric field comes out to be 2k lambda by r. Okay, very importantly, it's inversely proportional to r and radially outward. If you will have a top view, from this particular uh, infinitely long charge rod, this is how the electric field vector is going radially outward, and as far as you are going to go, the electric field is getting weaker and weaker as r will increase. Okay, so say this is that point P which is at a distance r. Okay guys, please keep the expression in mind, it's a very important expression, 2k lambda by r. So far we have spoken about uniformly charged sphere, we have spoken about uniformly charged hollow sphere, and now we have spoken about uniformly charged infinitely long rod. Okay, now the last object is a uniformly charged infinite sheet. So this is basically a sheet whose surfaces are going to go for an infinitely long length. Okay, you can think of it as a toilet paper roll being unwrapped. So this is how the sheet is going to go this side as well as on this side. So guys, very smartly we choose a Gaussian surface which is a cylinder, or you can call it a box also. Okay, this is basically your Gaussian surface. I want you people to keep the Gaussian surface what we are choosing specifically here in mind. And what you see here guys, for this plate, okay, if you try to look at its side view, if I look at it from this point, then the electric field lines are going to go like this, or I should say this is basically the source of a uniform electric field. Okay, this is your sheet, and this is basically the way electric field lines are going, and you are basically choosing a Gaussian surface something like this. This is what is happening over here. Okay guys, so now let's try to find out the expression of electric field, say at this point P we are interested in, which is at a distance r from the sheet itself. Okay, so now you see that this is basically the area which is enclosing some charge. So here Q in is what we are interested in finding, for which we consider that sigma, or you can say the surface charge density, Q by area, is basically a constant. Okay, so what we consider here, say this area over here, the circular area that you see, say this overall area is A. Okay guys, so I can say that the Q enclosed divided by A is also equal to sigma. So I can say that Q enclosed is going to be sigma into A. Okay. Now guys, have a look at the reasoning again in the same point. At this, in this Gaussian surface, there are again three such surfaces. So again, if I will divide E dot dA for the close integral, it will get divided into three areas. This one is area number 1, this is the curved surface area number 2, and this is your circular section area again 3. So you can see that there are two such circular areas which are 1 and 2. So for that, E into dA, the angle is going to be 0 degree. You can see that here the angle is 0 degree in both the cases, and here the angle is 90 degree. So for surface number 2, this was 1 and 3 by the way, for surface number 2, E dA into cos of 90 degree. So cos 90 is going to become 0. Cool. You can see that simple integration, and this is close integration. So guys, total flux is basically E into dA into cos of 0 degree, its integration, but such two surfaces are there, this curved surface, this circular section and this circular section. Both of them are having the flux non-zero. Okay, the electric flux is going out of it, and this should be equal to Q in by epsilon naught. So 2E integration of dA will be equal to Q in, that is sigma A by epsilon naught. And this integration of dA is going to give me the area of the circular section, which we have chosen to be A. Okay, so 2 into E into A will be equal to sigma A by epsilon naught. A gets cancelled. Electric field comes out to be sigma upon 2 epsilon naught, which, my dear friends, is basically a constant value. Doesn't matter how far that point P is, it is actually independent of this value of R. How far that point you are choosing, the electric field will come out to be a constant. As I said, a uniform charged sheet is going to become the source of a uniform or constant electric field. So because of this sheet only, the electric field lines are going to be uniform, and they are going to be equally spaced and are going to give you an uniform electric field value as well. Okay guys, so later on when we are going to study a chapter called as capacitance, that is where I'm going to tell you how the plane sheets are going to help us make or form a capacitor called as parallel plate capacitor as well. Okay guys, I hope you were able to understand all the four applications that we have talked about today. We spoke about the Gaussian surface application on a uniformly charged sphere, or you can say a non-conducting sphere. We spoke about a uniformly charged hollow sphere, or you can say a conducting sphere. We spoke about an infinitely long charged rod, which was again uniformly charged, and this fourth one, uniformly charged infinitely long sheet. So for the rod, the expression came out to be 2k lambda by r, and for a sheet, it came out to be a constant sigma upon 2 epsilon naught. That means electric field will depend upon the nature of the medium as well as the charge density, how heavily charged that particular sheet is. Okay, guys, cool. Okay, so for people who are watching this session and are basically preparing for JEE 2020, which is now happening in the month of July. I hope you guys are aware about that. So guys, we have a crash course which started this week on 11th of May. So on this crash course guys, we have 90 live classes going on for you, around 20 or more comprehensive tests along with assignments and detailed analysis is given to you. You will get unlimited doubt solving both inside and outside the classes. You can watch the replays and recordings of class if you ever miss. Obviously, important tips, rank booster quizzes, and previous paper analysis. So, guys, as I came up with a timetable also for you guys who are preparing for 2020, the 60 days timetable. If you are, I'm again repeating this part, that if you are not finding a timetable suitable for yourself, which I formed, or something that you made for yourself, then it's not the time to make and again, revamp your timetable. It's rather the time which is very important for you to utilize. If you are not able to work out on your own timetable, get into a routine by joining this crash course. Okay, so this crash course could be something which could be very helpful, and the amazing part is that it is not very expensive. All you have to do is go on this link, which is available in the description of this video, and remember this coupon code, that is SMCC. The crash course is actually worth rupees close to 25,000, and it can be yours for just under 6,000 rupees. Okay, guys. So do take this advantage. These are the steps that I want you people to keep in mind. The link, when you're going over here on the link which is available in the description. Okay. Step 1, click on enroll now. Use the coupon code and then apply the coupon code, that is SMCC. Okay, guys. Cool. Great. So I hope you will be able to take the advantage of this crash course, and definitely your chances of cracking the JEE examination in the month of July will, I'm sure, will improve significantly. Okay. Apart from that, guys, yes, I would like to share the previous year results. This is a very important and very catchy punchline which I like a lot. Before this particular situation which we all are right now into, yes, we are all homebound under the lockdown. This was last year when people, all these students, they actually could go out and study in a class, in a physical classroom, but they actually trusted Vedantu. And since then we say that, who says that you cannot crack the examination while being at your home itself? And now even when forcefully we are inside our houses, this should serve as an inspiration for all of you. Look at this, guys. Rajdeep Singh got All India rank 38 last year. Chirag Jain got All India rank 41 in JEE examination, and Sumit got the All India rank 1 in the PWD category. So, guys, if these three can crack this examination, even when there was no restriction of actually just studying at home through online medium, you guys are right now facing that situation, so you should be able to crack this examination because your intent is even more stronger and your resources are even more limited. But let Vedantu help you out, and let these guys serve as a source of inspiration for all of you. Okay, cool. So guys, I've told you about the crash course as well, and if you want to study, for people who are recently joined our channel and are not familiar about the topics which are already being done, and if you want to cover up topics which are done before, especially in electrostatics, if you want to cover electrostatics, the chapter which has been done so far, or the lectures which are being done already before this, all you have to do, guys, go on the playlist. Okay, on the playlist of this channel you will find all the lectures that I've done before. Look for this playlist, JEEt Law 2021, will find all the lectures over there. Okay, and if you want to not miss out on anything which is happening on the channel, we have a Telegram group as well. On this Telegram group we keep on sharing assignments and the solutions of that. Study material as well as daily updates are given over there. Yes, daily updates are very important. You don't miss anything if you are on the Telegram group. So how can I join it? Just go on the description, you will find the link for Telegram as well. Okay, so guys, I hope you enjoyed the applications of Gauss's law. We didn't solve any question today, but don't get disheartened. On Monday when I'm coming and I'm meeting you guys, we'll be solving a lot of questions. Yes, we will be solving questions based upon Gauss's law. Okay, so if you enjoyed this video, do press that like button, share with your friends, tell them that electrostatics is done, Gauss's law is going on, and if you have not subscribed yet, go ahead, subscribe as well as press the bell icon. Cool. So guys, this brings us to the end of this session. I'll see you again very soon. Till then, keep studying, keep smiling, keep enjoying. More importantly, stay safe. Okay? Bye bye. Take care, guys.